Okay, good morning to everyone. This is the second seminar of the webinar series of the Pangeafro Carval NOAA project. Today's speaker is Dr. Siomos Nikolaos, who will present Atlas tool, which is an automated software for Lidar processing. Nikos is a postdoctoral researcher working in the Ludwig Maximilian University of Munich. He has more than 12 years of cumulative hands-on experience with LiDAR systems, including development of corresponding software and QA/QC activities. Dr. Siomos is currently working at the Center for Aerosol Remote Sensing Unit of Actris, focusing on the QA/QC procedures to be followed by the participating LiDAR stations. Today, he will present the newly developed Atlas tool, which aims to facilitate the analysis of the QA tests of the network LiDARs. Atlas is publicly available and can be operated both centrally by cars and locally by the PIs of the stations for the processing of the routinely measurements of the systems. So this tool is going to be adapted by EarlyNet community for the LiDAR processing. So Nikos will give the presentation. You will be muted during the presentation, but you can write down all your questions in the chat. And after the presentation, all questions will be answered by Nikos, and you will be unmuted. And also the presentation will be recorded and will be uploading in the YouTube channel. So Nikos, the floor is yours.
Okay, thanks, Kelly. I will share my screen now. Okay. Do you see my presentation?
Yes.
Okay. So since Kelly covered more or less all the introductory stuff, I will just go directly to the algorithm itself. So the reason we prepared Atlas is mainly for the preparation and submission of the quality assurance tests that the Actris LiDAR stations measure to the Center of Aerosol Remote Sensing. So in the framework of this big infrastructure project Actris for aerosol clouds and trace gases remote sensing, the stations, the participating stations must be operational and they must provide an operational scale LiDAR products. And in order to achieve this, the quality of the measurements must be verified. So this is our role there in cars to verify that the systems are well performing. Apart from the strict Actris framework, we are also planning to cover the EarlyNet network stations, so the ones that are not tied directly to the Actris project, but were European LiDAR systems that were participating in the European LiDAR network EarlyNet. So this tool enables us to process and visualize the standard quality assurance tests, and this can be done also in a station level, so the PIs can process the measurements before submitting to cars and verify whether the measurements are of high quality already, so to avoid submitting measurements that are already quite problematic. And from our side, we receive the datasets and then verify again whether these measurements are indeed as they are expected, and the systems are fulfilling the network's standards. Atlas stands for Automated Lidar Analysis Software. The tool is developed in Python, and you can find the algorithm in the following repository. It is publicly available. So it is in a beta stage, so the algorithm operates. We won't encounter serious issues, but it's not totally finalized yet. At some point, I will move from this repository to a more official one. And the user interface, graphical user interface, is in preparation, also in Python, from our colleagues in INOE in Romania. We'll begin here with the flowchart of Atlas. So the first thing the user has to do is prepare the raw LiDAR data, and this usually includes the signals, the LiDAR signals, along with their metadata for each channel, and also metadata for the measurement. For example, when was the measurement performed, where was the measurement performed, and so on. Along with the LiDAR data, the user must submit also radio sound data, and currently only ASCII formats are supported, but the parser is quite flexible, so your ASCII format can be whatever. The algorithm can account for skipping lines in the beginning, also having different delimiters, and so on. The raw LiDAR data that are currently supported are the ones in the Lysel format. So Lysel is a company that is producing LiDAR recorders, and the format is endorsed by the LNet community in general, so we support it. And also PolXT LiDARs are supported. They are the second biggest community within LNet. So if your system has one of these two formats, you are already ready more or less to use Atlas. You can do it. The measurements we support are dark measurements with no light entering the telescope, the receiver. Normal measurements that are necessary for the relief tests, interleaf telecoverage, either in quadrants or rings, and delta 90 polarization calibration measurements. I will come to this later on. Atlas has three submodules that are processing sequentially. First, the converter is called, then preprocessor that does the preprocessing of the signals, and visualizer undertakes the plotting. So the input data is provided to the converter, and along with it, we might need also supplementary data, such as additional channel info that cannot be provided from the raw file headers, or also station info that is also external to the raw LiDAR data. This information is parsed in the algorithm through the configuration file, and it is also possible to provide here information that is already available to the raw file header in order to override the header. This information goes directly to the converter and none of the other submodules. Along with it, we also need a settings file. So the settings file has different options for the algorithm. For example, for the converter, how the radio sound file is formatted, these sort of options are set in the settings. For the preprocessing, information such as which is the altitude range that the algorithm will process, up to how many kilometers. For the plots, there are different options per test, because each test has different requirements. For example, for the relief test, the user needs a molecular region, has to define it. For the telecover test, the user must define a region where above the full, well above the full overlap, as an example. And all of these options there have default values, so it is not totally mandatory, but in most cases you have to fill at least some of these informations there. And as a last piece, some information is passed to the algorithm as arguments, command line arguments, in order to be able to process a lot of measurements from the command line automatically. These arguments include usually the paths. For example, where are the measurements placed and where is the radius and folder placed, and also which is the file format. Is it Lyser or PolXT? So after providing all this information, the user can actually run Atlas. And at this stage, I want to mention that graphical user interface is under development by Victor Nicolai in INOE. So the graphical user interface will undertake all this configuration and settings files, and options will be passed through it. You can see an example on the right. So the graphical user interface is not yet fully operational, but there is some work that has been done, and you can see how it will be. So, for example, in Atlas settings tab, the user can more or less create the settings file, and by pressing write configuration file is generated. Similarly, with the write settings file, a settings file is generated, and the user can select whether they want to run directly the algorithm from the graphical user interface, or just use the configuration files to run it from command line in case they want to process a lot of data. So it is quite flexible. The user interface is a wrapper for the command line, and the two algorithms are developed separately from one another. And we also plan to also support integration of the handbook of instruments. So this handbook of instruments is a database that is also coupled with a single calculus chain algorithm of actors, and has a lot of metadata, contains a lot of metadata for all the stations there. And ideally, we would want to fetch those data directly from there, not to put them manually. So the next step is to instead of providing manual input there, to interrogate the handbook of instruments. This would be done probably by the end of this year. The output files that we get from Atlas from the first to the converter stage are the QA and HDF files that the users have to submit to us, to CARS, and there is one file per quality assurance test and also for the radio sound. The preprocessor generates some intermediate files that contain the preprocessed signals mainly for debugging purposes, and they are also used as input to the visualizer that creates the plots, and also ASCII files in the old quality assurance format. The user can also select if they want to process fast after an initial processing, they can just call the visualizer and use the already available output files from the previous analysis from the preprocessor to speed up the processing. This is also a possibility. So as said, the quality assurance HDF files will be submitted to CARS, and we also plan them to be simple calculus chain compatible. So right now, the user should upload only to the CARS database. It's called CARPort. In the far future, single calculus chain might undertake this part. So far future means more than 3 years afterwards, or so on. So we account for it that these files are in a format that is recognized by the single calculus chain for now. The intermediate files are in general useful for debugging, but in general you don't need them after finished processing with measurement. You just can delete them. And the quality assurance ASCII files are in the old format that Volker Freudenthal was using to do the quality assurance of the ELNet network. It's just ASCII files with columns per signal and some metadata. So moving to the more interesting part, the tests themselves, we will start with the quick looks. And although they are not quality assurance tests literally, they are quite useful in providing qualitative information of problems that we might encounter really fast. So they give a very good overview of the signal evolution through time and through the vertical range. The first thing one can see in a quick look is the cloud contamination, and this is always a problem for LiDAR aerosol retrievals, especially if the clouds are low and we don't have there is no molecular region before the cloud that is necessary for the relay fit test and also the depolarization calibration. So the high cloud usually are not a problem. In any case, with a quick look, the user can decide whether they want to throw out this measurement entirely or just keep part of it. Another thing one can see in a quick look easily is the gaps. So by having just a file, LiDAR files usually contain a lot of information inside, 3D information, and it is not easy to see if there were gaps. Quick look is an excellent tool to visualize whether the LiDAR stopped for some reason and see whether this gap is large or small and can be tolerated or not. We can also detect easily what is happening with the solar background and whether this is a problem or not. For example, looking at the case here below in the lower graph, you can see that in the first part of the measurement, there is some signal from 5 to 14 kilometers, but later on, the noise starts increasing and we have higher values and very low values. This is indicative of noise. And this layer here is less and less visible. So looking also at the time in UTC, this means that the LiDAR has the dawn, there is already dawn, and the solar background is adding additional noise to the measurement. So this noise can be destructive for Raman channels, and it is always good to know what was the status of the measurement, which part was in daytime conditions, which part was in nighttime conditions, and decide whether we want to throw this measurement entirely away or keep it. We can also see things about the atmospheric turbulence. You can see here, for example, in the boundary layer, there is a lot of activity. And for some tests, for example, for the telecover test, we don't want this. So already from a quick look, we might decide that we don't want to make a telecover test for this data, or we won't consider it. We will get noisy information. Other malfunctions can also be visible, not in those two cases here, but in general, you can see if there are issues with the laser power. This is usually a very smooth decrease of the signal level, so the colors change in the whole vertical range smoothly with time. This indicates that the laser starts becoming misaligned, or that the intensity for some reason is affected. Spikes can also be visible sometimes here if they are large enough, and noise patterns might be visible in the far range where no aerosol are expected. And in general, we support quick looks also for the other tests, not only for the normal measurements, but also for the recover test. You can see an example here for each sectors sequentially, that performed sequentially. And also for the polarization calibration that usually has two parts. We can see if there were clouds in any of these parts and if there were problems there. So moving to the actual quality assurance test, we will start with the most basic one, the really fit test that can be performed directly in any LiDAR measurement, normal measurement. And before going to it directly, we will mention that we need molecular information. So a molecular attenuated backscatter profile is needed. For this reason, we use a dedicated algorithm called ARC, developed also in LMU. It stands for Algorithm for Rayleigh Calculations. So this algorithm requires information about the air composition, molar fractions of the molecules this time. So nitrogen, oxygen is supported, argon, carbon dioxide, and water vapor. The temperature must be also provided for the rotational Raman calculations. The incident wavelength, an interference filter. So these sort of filters are usually deployed by LiDAR systems per channel in order to suppress the background radiation. They also suppress, as you can see on the left here, the rotational Raman lines. In this example on the left, you can see what happens after scattering from the air molecules. So part of the most part of light is polarized with this red line, and the blue lines are the depolarized, the light coming from depolarized scattering. This depolarized scattering is only due to rotational Raman scattering. As you can see, the two wings are formed, the anti-Stokes branch and the Stokes branch, but there is also a third branch here in the middle with lines that fall exactly at the same wavelength as the polarized line. So polarized and depolarized line in the elastic wavelength, the 355 nanometers, the original wavelength, consists the Caban's line in general. And by using an interference filter here, I will show you an example next. Some of these lines that are highly depolarized are suppressed, and this changes the depolarization ratio of molecules. And depending on the temperature, the cross sections of these lines increase for higher wavelengths and decrease for lower wavelengths. So one in general needs an algorithm to do these sort of calculations to get in the end the final cross sections for the scattering and the backscattering, and also for the depolarization ratio. In addition, the user can also define the amount of lines. Usually 41, more than 41 lines is sufficient. And the pressure levels if the user wants also to get the scattering and backscattering coefficients. We need such an algorithm because, as you can see, the polarized cross sections change with wavelength, and the total amount of depolarized cross section also changes with wavelength in a similar manner, let's say. And the cross section of the lines also change with wavelength. I have an example here of what happens when an interference filter, this yellow line, is used. As you can see, the interference filter suppresses lets the Kaban line pass through with its polarized part and its depolarized part, and suppresses the wings. And you can imagine now that if we have a lower temperature, then these wings will be more centered towards the center of so larger cross sections will take place in wavelengths closer to the original one, and the depolarization, the light that passes through from the filter will be more depolarized than for higher temperatures. So we use ARC for this sort of calculations. For the layer fit, we don't use the depolarization, we just use the cross sections. To calculate this red line here, this is what we want to do. The red line is the molecular attenuated backscatter profile, which is our reference. And we select one region to normalize the blue line, which is the Lidar attenuated backscatter profile with the molecular one. And if there are no misalignment issues in the far range or other strange issues, then the signals must agree in the normalization range and also above it. So you can see for the case here above, there is a good agreement between the two lines up to 14 kilometers more or less, taking also into account the noise levels. For the second case here below, you can see that, okay, in the fitting range, usually we have some agreement, although you can also see that there are some layers here. And going away from this range, you can see that there is a systematic underestimation of the measured profile in comparison with the theoretical attenuated backscatter profile. So in those cases, this is a clear indication of misalignment. It shows that we are losing signal in the far range. In that case, the user needs to realign. So if we would receive such a measurement, we would tell the users, the PIs, that okay, your system is misaligned in the far range, please misalign it and send us again the datasets. Right now, this range is manually, the really fit range is manually provided. In the quite near future, actually, I want to add this molecular mask generated by, the code is by Volker Freudenthaler. So this algorithm uses different statistical tests that show whether the distribution is of points is Gaussian, so the noise is is only Gaussian and not aerosol. Checks the slope of the two signals, the net backscatter signals, whether the slopes agree. There are other tests like this cross test that checks whether at some point some regions get systematically below the molecular line, given a normalization point that is below that altitude. So in the end, the user gets a molecular mask. So these blue points here are recognized as a molecular region. And we plan to add this sim in Atlas 2 to do the identification of the reference height, the height where only molecules exist, automatically. Moving on to the telecover test. So checking the alignment in the far ends is done by the really fit test, but one has also to take into account the telecover test to see what are the conditions in the near range, because the far range might be satisfied, let's say, no misalignment there, but still we might have overlap issues in the near range that are could also be related to misalignment or not optimal alignment, let's say, of the system. So most of you are familiar with the telecover test. It can be either performed in sectors, like in the right plot, or in rings, like in the left plot. When using sectors, we use the north sector is defined as the sector closer to the laser, and then we go from north, east, southwest, going from left to the right. And so by comparing the signals from the four sectors, we can get a good estimate of the full overlap range. So by normalizing the signals from the sectors, because it's necessary to normalize because the intensities are in general different, we compare them to one another and see whether they agree above a certain range. So for this case, for example, we try first 2 kilometers range that it will for sure be above the full overlap range that is already also available from the manufacturer. So we normalize at 2 kilometers and then check what is happening below. And we see that the signals variate due to noise, but they are well below this 5% deviation limit, down to 200 meters more or less, and even 100 meters. Then the signals start to deviate. This indicates here, this shows us that we are entering the overlap region, and this is the limit of where we can trust our signals in the near range. The shadow that you see here indicates the atmospheric variability. So interleaved tests are supported. Interleaved means that the user makes northeast southwest measurement, and then again one round of northeast southwest, and then again one round. So the individual north sectors are compared with each other, and the variability within those sectors can be is plotted here with the shade for sector. For example, you can see that there was a lot of variability here for the blue one for the east sector. So atmospheric conditions changed at some point when we were performing the east sector measurements. It can be used as an indication to see whether the atmosphere was very variable, and if it was very variable, then we cannot draw firm conclusions because some deviations here that are due to the full overlap, the overlap of the system, could be hidden by layer patterns that appear only in a specific section and not in the other ones. So in a combination, we use this test in combination with relay fit to verify that the alignment of the system is optimal. And moving to the last test, the polarization and calibration. The user must perform a delta 90 calibration for the systems. I have a schematic here. So this is a LiDAR system in boxes, starting with the laser, the emission optics, the atmosphere, the receiver optics, the calibrator, and the polarizing beam splitter that can be a cube or other mechanism. So the calibrator can be placed in different positions, and you can find more information in the paper of Volker et al. 2016. For visualization, I have here the case where the calibrator is just before the beam splitter cube. So this measurement, the delta 90 calibration, must be performed at two angles that are exactly 90 degrees apart from the zero position. You can see an example here of in the Polish LiDAR system. This is the zero position. You can see that the receiver here is placed at zero. This orientation we define as zero, and then we make a measurement at minus 45 degrees. So you can see that the whole receiving part is rotated at minus 45 degrees, and then again at plus 45 degrees. And if one uses does this mechanically, they have very good accuracy in these two angles. Then they are 90 degrees apart, and when we are calculating calibration factor of the system, the errors are compensated, and we get quite good estimate calculation of this parameter. Once again, I will stress here that molecular depolarization ratio calculations must be done because we also want to, after performing the calibration, we want to verify whether it was successful by comparing with molecular values. So for this reason, we also use ARC again. You can see here an example. I did some calculations with different interference filters, and you can see that the depolarization ratio profile of the molecules is expected to change with height. If the interference filter is quite small, the profile is more or less stable. But for larger interference filters, for example, for 1 nanometer here, you can see that we can expect some temperature dependence that can be visible even in the measurements if the noise is low. So on here, let's focus on the upper plot. On the left, you can see the calibration, delta 90 calibration. So from this one, we get eta, actually eta star. So this is a calculation, first calculation of the calibration factor, and then we have to perform a correction that has to do with the crosstalk in our systems. So some systems have crosstalk, some others not. If the the polarizing beam splitter is cleaned, then we don't need to do this correction. If it is not cleaned, for example, PolXT systems do not have a cleaned analyzer, then this K value must be theoretically calculated or calculated from experimental values provided by the manufacturers, but not from the LiDAR people themselves directly. Then we can make a correction and correct and get the real calibration factor. With the red line, you can see the plus 45 signal and the minus 45 signal. As you can see, there is some mismatch between them. The truth is in between. If these two angles are exactly at 90 degrees apart, and we get the mean value here as the value of the calibration factor. From the difference of the two signals, the plus 45, the two signal ratios at plus 45 and minus 45, one can get an estimate of the misalignment angle of the polarization of the laser, this epsilon angle. This is just a guess, let's say. It relies on assumptions of how the system is and assumes that the receiver optics are ideal. More or less, it gives us the orientation of the laser, the linear polarization, with respect to the polarizing beam splitter axis, reference axis, of the light that is incoming to the that arrives in the calibrator surface. This is what we get here, more or less. And then we can, depending on how the system, the setup is, we can relate it to a misalignment of the laser or not. Then going on the right, we apply the calibration factor, and then we compare a measurement. So this orange profile is measured, and the green profile is the one from the molecules. You can see here that this profile changes a bit with height because of the temperature changes and the interference filter that is applied. So the measured profile is then corrected using the GHK parameters. So it's not possible to cover this here. You have to relate to the paper of Volker to see what exactly are these parameters. In principle, the user can use these 4 parameters to correct for issues in the receiving optics and the emission optics or the LiDAR, the laser itself, as long as they know what these problems are, either from the manufacturer, for example, the attenuation of the receiving optics, or some depolarization from the laser itself. You can see here for this correction, we have used values that do not change much the depolarization ratio. So the corrected profile is more or less similar to the measured one. I have here another example. You can see a measurement from another system here below, and the noise levels here are much decreased. The misalignment is much less. In general, this misalignment is not a problem for the calibration as long as it is lower than 2 degrees, let's say. K is 1, so the calibration is quite fine here. But when we apply the calibration factor, we see a large offset compared to the molecular profile. And as you can see here, we haven't applied a GHK correction because everything is 1 or minus 1. So this sort of offset can be attributed to the laser because we are looking at 532 nanometers, which is the second harmonic. So this laser is producing also a third harmonic at 355 nanometers. And in that case, the second harmonic is expected to be a bit depolarized. So this is what we're looking at here, most probably, depolarization from the laser itself. So in that case, the GHK must be calculated again, taking this depolarization into account. And ideally, we should put the laser in the LEM to verify that this, what we measure from the atmosphere, is the degree of polarization that we get also from the LEM. So I'm about to finish my presentation. Just want to repeat some take-home messages for you. So if your system has a license recorders, or if it is a PolXT, then you can directly use Atlas. And I think that you already got by now that quality assurance tests ensure good performance of the LiDAR system, and most importantly, warn us of problematic cases in order not to throw them away, and correct issues in the systems. The laser alignment with respect to the telescope is critical and must be checked, even at for each measurement even. It is not possible to calculate any polarization products if we don't do a polarization calibration. I showed you before the volume depolarization ratio profile, but it is even more critical to have a good volume depolarization ratio profile to go to a particle depolarization ratio profile, where all errors are more enhanced. If any of you is interested in testing, we are inviting you to do so and post any bugs that you will find in the ELNet forum. And in case you didn't already notice, there is a hands-on training taking place in Bucharest in June. It is a bit late now to participate physically, but I think you can still participate online. So you have to inform Doina Nikolai or contact me not to give you more details about the hands-on. So thanks a lot for your attention. And are there any questions?
Thank you, Nikos, for this interesting presentation. I cannot see any question in the chat. Perstera has one question.
Perstera, you can ask for your question.
Yes, Nico, in slide 22, I think. Not 22, sorry. About one before. About the changes, the different depolarization values at different heights. Are these differences attributed to the changing of temperature? I mean, of the shifting of the Kanban's, the wings and the Kanban's line?
Yes, Perister, exactly. It's a combination of temperature and also of the shape of the filter. So, for example, for very narrow filters, we isolate the Kanban's line, so there is no temperature dependence because the filter throws away the whole wings and nothing changes more or less there. For very broad filters, then the whole spectrum is included in the filter, and still there is no significant change with temperature. This also has to do with the original wavelength. So the Raman lines are broader from one another for larger wavelengths. So this is the case for 355. For 164, you could see a very different plot for the same interference filter widths. And for 355, you can see that intermediate filters, in the order of 1 or 2 nanometers, have the most temperature dependence because more or less their edges fall here with close to the maximum intensity of the rotational Raman lines, and where temperature is creating the strongest effect.
Thank you.
Alexandra?
Hello, hello, Nico. Can I ask about the calibration of the polarization calibration of polyXT? You mentioned that there should be some different calculations or calculation of specific coefficient for the depolarization calibration of polyXT. Is this because it measures the total and the cross signal and not the cross and the polar, or because it uses some kind of optics that it is not characterized well? I don't know. What is the reason?
It is the first reason mainly. So when one is measuring the total signal, it is impossible to clean it. When measuring cross and parallel, cleaning is possible. So cleaning means that usually the polarizing beam splitters, for example, the cubes, separate parallel and cross radiation into different paths, but there is some crosstalk. And in order to reduce further this crosstalk, then we use a polarizer in the parallel channel and an additional polarizer in the receiving channel to remove any crosstalks from the other polarization orientation. In polyXT systems, there is a cross channel. That, let's say that this one could be cleaned with a double or a very good polarizer. And but the total channel cannot be cleaned because there is no polarizer there in general. So the idea is that if there are issues in the detection optics, these issues affect the calibration. So the calibration factor in that case depends on the receiving optics, also on the it depends on the polarization state that is arriving. This is the main problem. And in those cases, the user has to calculate this K parameter to correct the calibration factor that they use, because then the measurement is not totally representative of the real calibration factor. Does this answer your question?
Yeah, so there is, you mean that there may be crosstalk from the cross-polarized channel into the total, so poly measures the total, but also some crosstalk from the cross channel, or that you cannot, yeah.
Yeah, so let's imagine an example. We have a case with non-depolarizing aerosols. So when this the radiation from the atmosphere passes through the detector, if there is deattenuation, this affects the state of polarization differently than when light comes depolarized, for example, when we have dust in the atmosphere. So in that cases, the Stokes vector that, in general, the Stokes vector that arrives in the receiver is different. So the depolarization levels are different, and they are further affected by the receiving optics. They are also defined by the atmosphere. If there is a crosstalk, the crosstalk would be enhanced if we have more depolarization. For example, in the crosstalk of cross polarization in the parallel channel would be enhanced. For the total channel, for the total channel now, the attenuation also causes decreases to total intensity. So if the receiver optics are introduce deattenuation, this would affect in a different way the total intensity that we will receive in the total channel.
Okay, so sorry, it's not the traditional crosstalk. It's the effect of the optics when you measure the total channel, or when you measure the cross channel, and you can avoid this if you measure cross and parallel separately. But when you measure total and cross, you cannot really separate. I don't know. You cannot really. Okay, let's not.
It is both more or less. So even if you have parallel and cross measurements and you don't clean, so the crosstalk there is significant. You don't do any cleaning, then you will get effects from the atmospheric state of polarization in the calibration factor. If you measure total the total signal, then your system is sensitive to the deattenuation, because the deattenuation will cause different attenuation depending on the degree of polarization in the profile.
Okay.
And then the total signal will be problematic, and in that cases the user will not even detect it. So it is usually preferable to measure parallel and cross and not total and cross.
Okay, and sorry, and my last question is this coefficient that you use for polyXT to calibrate the polarization signal. You said that this is based on manufacturing values for the optical parts, and okay, so we know that usually these values are not the optimum estimations of what happens in reality. So there is no way we can measure this coefficient by ourselves in poly and really characterize fully characterize the polarization signals and be sure that we have the correct coefficient for correcting the polarization signals.
So in a general case, in a general system, there is no easy answer. But and if no additional measurements are performed, it's difficult to say. But if one has the ability to make a polarization calibration before just before the polarismic splitter and also before the receiving optics, and also have the emission well defined, so that we know what is happening with the attenuation and what is happening also in the emission state. Then it is possible to calculate this K also experimentally. But this also requires additional steps. For example, in the polystick XT system, that they are performing this calibration in front of the receiving optics. So a solution would be to add a calibrator before the beam splitting part and make an additional delta 90 there. In that case, you can compare the two delta 90 calibrations, and from the difference quantify the deattenuation, and then add this deattenuation to the theoretical calculation, let's say, of K. So in the end, you measure the independent parameters. You have to have these parameters from somehow from somewhere, either from the manufacturer or from doing it experimentally with this sort of techniques. And we must rely in that case in molecular regions, because aerosols are unpredictable. So we can only rely in molecular regions, and even then we have to know the state of polarization of the emitted laser beam.
Okay, so it's feasible to measure it experimentally.
Yes, it is possible. Yes, it depends also a lot on the system, and yeah.
Okay, thank you.
You're welcome.
Nico, I have to ask you more about this topic that Alexandra raised. I was hoping we leave our own questions for the last, so that we give priority to the other people. But now that we are here, the K value is, first of all, the poly systems, they have the polarization in front of the beam splitters. No, in front of the beam splitters in the receiving point. So it is exactly after the telescope, after the secondary mirror.
It is here.
Yeah. And then in the K that we measure, the K that we will measure in the end from the tests will have to be different for different atmospheric conditions, for different aerosols above the atmosphere, but also it will have to be different for different loads, based on what you mentioned before. So in the end, if we cannot measure it just one time and then we use this to apply it for all the measurements, because it will be different, the K that we will have in a clear, in a marine environment, and it will be different, the K we will have in a dust case.
Yeah, Lenny, depending on the system. So for polyXTs and the specific, yes, for polyXT systems with a setup similar to yours, this is true. The K parameter depends lightly on the aerosol type and load. Actually, it depends on the volume depolarization ratio. So the volume depolarization ratio is a combination of both the aerosol load and the aerosol type. So in that case, what they are doing now in the cyclic calculus chain, you calculate a polynomial using the scripts of Volcker, the GHK scripts of Volcker. You can calculate a polynomial correction of for the K, and have the K value in different volume depolarization ratios. Yeah, the correction can be a bit tricky though, because in order to get the volume depolarization ratio, you have to have the K. So it is like a chicken and the egg problem sometimes, but I think you can perform iterations to get to an optimum.
Eleni, sorry, if you remember, when we did these measurements for poly, Volcker gave us a number of K parameters for different volume depolarization values. And then in the end, we said we will compromise for a single value, depending on the scenarios we usually have for the station, like dusty or non-dusty, or in our case.
Yes, Anna, I remember, that's why I asked, because in the end, but this K was measured one day with relatively clear conditions, in the extent that we didn't have dust at that point. So what Nikos is mentioning here is that But these measurements were not, that if we measure exactly the same parameter, if we follow the same approach, and we measure again, but we measure in a dusty environment with more, with higher depolarization, volume depolarization measurements, maybe then the calculations, the K calculation there will end up different.
We did the measurements, but the other values I understand are based on theoretical calculations. Like you did the measurements for this specific case and your volume depolarization was that. But if you have volume depolarization this, then your K parameter should be that. Because we didn't do 5 different measurements and we didn't have 5 different volume polarization ratios measured on that day, we had just a single value. But in the end, we ended up with 5 different K values for 5 different volume dipole.
So if you do,
So this is very detailed now, specifically for our system. But the general question is that if we need 5 different measurements in different environments to get the different Ks for the different volume depolarization ratio conditions.
Yeah, Ellen, it's not so specific actually, because this feature is implemented in more or less all the PolyXT systems, so it is relevant to many systems. So I wasn't actively participating in that discussion at that point of what exactly you tested when Volker was calculating the parameters for your system. One solution is to somehow perform a delta 90 calculation here after the receiver optics. In that case, you will be able to measure the deattenuation experimentally and not from the beam splitter values you get from the manufacturers. This is always a step forward. You will not get rid of the attenuation of the change of the K value depending on the volume depolarization, but you will probably have a better estimate of the overload attenuation or of any other problems that might be there in the receiver optics. An even better solution, though, would be at some point to replace the total channel in PolyXT systems with remove the polarizer there and just put a PBS there. It is in that way it is also more easy to reference the system, to have a reference orientation. Now the reference orientation in PolyXT system is the polarizer of the cross, and there is no 90 degrees orientation perpendicular to it, so just the total signal. So this angle with respect to the laser is critical also for the calibration of PolyXT systems.
We have at some point in the system, before it is emitted, before it leaves after the laser and after the second and third harmonic generator, we have a clear polarization cleaner, where everything is supposed to everything's supposed to change them in one direction, in one polarization direction, and then send them upwards. So this is so when you start having one specific direction, and then after the receiving, then you get the total with all the problems you mentioned and the cross. So you think it is best if we totally change the total channel with a cross with a parallel one only?
It is always beneficial, yeah, because then you don't need to care about K anymore again. And you can always construct the total signal, total channel based on the. Actually, you get always a better cross. In your cases, you should also, if you have the attenuation, you should always correct the total backscatter. The total signal must be corrected for this attenuation, because it is not a problem only of the depolarization. It is also affect the signal levels, and it affects the signals differently for different in the molecular region, for example, and in the dust layer. So you will get some small structures, not very huge effects, but you will get some small structures in your total backscatter because you are measuring an unclean total.
And how much is the effect? How much is the effect that you expect, the percentage of its effect in the measurements?
Depends. Under severe detonation conditions, that is not very typical for modern systems. I don't know. I remember in the past, INA has done a study, but in a system that was severely affected, I have the feeling of something like maybe even 20% for dust, but I'm not sure. I don't remember exactly. So if your detonation is very small, which is in general expected for newer optics, in general, then you won't have such a big effect. And it is also more pronounced if the aerosol type changes a lot. So you have dust and then marine, for example, and then molecular. Then you can expect larger differences. If it is marine and then molecular, because the polarization ratio is more or less the same, you won't see much of a change. So the whole signal will be decreased or increased due to the detonation, and you won't see structural differences.
If it is marine, you don't have much, because you said that it has to do with the volume depolarization, and there you have also, then it will be negligible there.
Yeah, so these effects are pronounced when the volume depolarization changes a lot with height. Because the detonation has a stronger effect, the stronger the depolarization is.
You mentioned about the GH gauge in this topic. You mentioned about the GH gauge that and the possibility to measure it for that maybe you need to re-measure them. So this is the procedure that we have to measure in different conditions and then see how, if this changes and if these calculations that the projection, if these projections are accurate in different atmospheric conditions.
So the GHK, the G and H, let's say correction. Leave the K outside for this. So G and H should usually be stable. You should check them again when you do major changes in your system. For example, if you change an optic, for sure you have to calculate again. Or if you change the laser, if you realign the laser is not critical, but if you change the flash lamps, for example, or change an optic in the emission or anything, you have to calculate again the G and H parameters. Then they should stay the same for a long time until something is degraded or so. You can always check this is a good test to compare with the molecular atmosphere. If you see that in molecular regions, the depolarization ratio that you measure with a specific GH correction is always the same. You measure always the same offset. In our case here, how much is the offset? This 0.0091, while the molecular is 0.0073. This is a good indication that nothing changed in your system. And if you also measure a constant calibration factor, it's a good indication.
But can you hear this here? Shouldn't it be the orange on top of the green in the molecular?
It should be, yeah. In this step, we didn't do the correction for the depolarization of the laser itself. So what you see here is most probably, I cannot verify 100% because you can see there is a cloud here. So it is either small aerosol layers, but most probably it is the natural depolarization of the laser. And I'm more persuaded about this because, as you can see, the green line is increasing a bit with height, and this orange region is also following this increase. So this means that probably here we have a dominant, we have still a strong molecular signal, let's say.
So, Nikos, these plots are provided from the atlas to the user? Okay.
Yeah.
Okay.
So, Nico, if we see these plots, if we see a plot like the lower one, not the top one that has the cloud, and okay, you cannot have a good information, but if you have an output like the lower one, is it a problem? So should we check what we should do, how we should have different GH, what we are defining wrong there, because they should be the same, or it should be something that you mentioned before about the effect of polarization in 532 channels due to the 355 conversion in the third harmonic?
Even in that case, you can correct for it. So the offset here is big. If you verify for sure, so when you see an issue in this plot, it is indicative that there is a problem. It is not always, it will not tell you exactly what the problem is. It gives you an indication of where to search. So my first guess here, depending on the levels of the offset, would be the laser. So what I would do is find an independent way to measure the polarization, state of polarization of the laser, which is LM. And if you do this and you verify that this is the problem, then you can use this value here to calculate again so include the laser depolarization, the impurities of the laser in the GHC correction. This is possible, and then you will see that if you do it, the orange line will get down to the green line, and in that case, we just have. So we will have a good volume depolarization profile, but you cannot avoid having some, let's say, molecular noise because you have some background coming from the molecules from the depolarization of the laser. Actually, when you subtract it, you will not get rid of the random noise introduced of this extra, let's say, background that you have there. So what I want to say is that, okay, you can correct a measurement that has 0.15, like 15% volume depolarization offset. But then if your aerosol layers are in the order, the depolarization is in the order of 0.04, much lower, the signal will be quite noisy because of the high background, and you could not see fine structures. So it is best to have always small depolarization from the laser. Yeah. In addition, in this example I gave, if you see a 0.15 offset, this is not the laser, this is something else. Probably a beam expander or some sort of window. I just gave an example. Yeah.
Nico, so with the LEM, you can measure the GH of the laser. If a laser has inside the second and third harmonic, so if the second and third harmonic generator is inside in the front of the laser, but in some poly-XT systems, polytype systems, the second and third harmonic generators are in front of the laser. So there, even if you measure the laser separately, you will not see this effect. You have to measure after the second and third harmonic when all the laser beams have been created. Is this possible with LM?
In principle, yes. So it depends on the size. Usually, yes. The LEM I have in my mind now. So there is you can mount the laser outside of the LEM platform and then align the LEM with the laser, and I think you will be fine. Yeah. So from the LEM, you will get one of the pieces you need for the G and H correction. So I will go back to this figure. There are different pieces here that all participate in the GH correction. The laser, the emission optics, the receiver optics. So in principle, the best thing to have is to have the Muir matrix, for example, for the receiver optics, the Muir matrix for the emission optics, and the Stokes vector of the emitted laser. Because this is impossible, more or less. It is very difficult to get the full Muir matrix. We focus on the most, let's say, the most problematic, what is more possible to happen. So, for example, the receiver optic is usually a combination of retarding the attenuators. So you expect an overall deattenuation and an overall retardation. If you manage to measure both of them, then you have a full description of the receiver optics. And the problems in the emissions, usually you try to solve them. So if a glass here is causing emission problems, you try to put another glass there that is not introducing problems. You don't want, in general, problems in the emission. The only thing that you cannot do anything about it is the laser, usually. In poly-XT systems, I have the feeling that you clean all three wavelengths in the emission because you use this trick, the Glenn polarizer. So in that case, I wouldn't expect in your system such a big offset for the 532.
And also if you measure after the secondary mirror, after the secondary mirror, then you find no effect there. That means that the first part with the laser is okay because you are clean up to the point before the receiver optics.
Yeah,
Then the first part is okay.
but since you are using a cleaner now, the thing is that each time you move the laser out and you put it in again, if it's not placed at exactly the same position as it was, then the outgoing, the degree of polarization in the outgoing beam might be a bit affected. So ideally, yeah, you can always, then again, this is not a big issue. If everything else is solved, the receiver optics, that is the most important thing, and the cleaning, also measuring the K, and we are sure that only the laser is left, you can always use this measurement here. So in the end, we will have such a small offset here, and then you can, if you see it systematically, you decide it's from the laser itself, and then you use it to correct for it.
Nico, one more question about slide 16.
Yes.
Here you have in the lower plot that you said that this relief feed would shows a problem and you would return it back to the people to check again. Here you have the distance from the Lidar up to 24 kilometers. So actually,
Can you make it in full screen?
Yeah.
In order to see it better. Sorry, Eleni.
So this now is up to 24 kilometers. So, and the above is up to 14 kilometers. So is it, should we check up to 24 kilometers? Is this the height that we should have the good molecular convergence?
Yeah, in general, the higher the better. Yes.
But I guess the problem starts even lower.
Yeah, it is not so visible here. So from 10 to 14, around 14, I can see there is some deviation here in this plot. It goes a bit below, but because the noise, so the relief fit has always to do with the noise. If the noise is large, then it is difficult to see patterns. And there are also, so in my simple approach, using just one range and then check what is happening, a lot of things can be missed. So this is why we are going to use the automated module, because here there are checks like the slope check, where you compare something that is not easily visible here, compare how the slope of the red line is different than the slope of the blue line within this specific range, and also other statistical tests to see if there are structures and so on. So in general, yeah, I would look as high as possible to see if there is, if the noise, for example, is statistically significantly deviating. The two signals here are deviating. But in the future, I would rely on this one.
And one more question, specifically for this one that you said. So from slide 17. So this you will include it in this one. You will include it in the SSE. No, this the next one. This one you will include it in the SSE, and there is a possibility that you find a clean aerosol molecular region, and then above you have elevated layers, like from smoke layers, for example, for Canada, wildfires or dust layers, and maybe you have a clean conditions below that. How this will affect the retrievals in the end that will provide to the sea? Then this will mean that everything above this region will be skipped, right?
Yeah, actually, so now testing falls mostly to Volker and Ina within the SEC. Ina is implementing it in her ELDA multi-wavelength module, and I'm pushing them to have maybe at least something for the in the development itself, at least to test. Also, maybe later on integrated for the Atmo access, but it's still under the discussion. In any case, as you said, and as you can see also in this plot, it is possible. Yes, here you can see a cloud, and the reference, the molecular region is detected below the cloud. So in principle, elevated layers will not be a problem as long as there are regions that are molecular. And it is also a success if the module does not find any molecular region when there are a lot of layers in the atmosphere, and it's difficult to find such a region. We would
So
also
you
like
will
to
find
know,
several more. Sorry.
yeah, we would, in that case, if there are a lot of aerosol layers and not large molecular regions or no molecular region at all where the signal is not very noisy, then me personally would like to throw away such a measurement automatically.
So, but okay, so here I see that there is one region that fits all criteria, but a little higher, for example, at 12 to 14 kilometers, or at yes, at around there. There are also several of the filters that there are several of the filters that they are fulfilled, except of the for the green one. So then maybe this is a possible. I mean, maybe not all filters need to be for these cases, for the elevated layer cases. Maybe you should consider not having all the filters, but a compromise with a lot of the filters that which will accept the layers, or else we will not have in the network any measurements from elevated layers. From smoke, we will have no measurements.
Won't it provide several molecular regions, and as a user you can choose?
Yeah, so okay, this goes to the discussion we had in the SEC. So the failing criterion here is the root mean square error. So this means root mean square error is not exactly noise though. It means, yeah, if there is large deviations due to noise, it reflects to the root mean square error. So there is a possibility that this criterion here is relaxed. So instead of having it as a limiting factor, providing it as an indication of the quality of the mask.
No,
Yeah.
like what Eleni said, like notify the user that this and that criteria didn't pass, and this might mean whatever for your measurements, and you are able to choose.
Anna, what you are missing from the last months in Actris is that they try to limit the users to any changes. So what they actually now also for the AtMax's campaigns we will have, they plan to not even allow to the users to change the reference heights. So the target is that everything is automatic, and then in the end, and the users not have the possibility to, the operators not have the possibility to change the reference height if they see that something is wrong and the retrieval is not accurately derived. And then after the exercise, then they collect the cases that it was the problem and try again to improve the automatic way for better retrievals. So this is the plan, the centralized plan now for Actris, and that's why I ask this here also, because we should make sure that this will not limit the elevated layer measurements, which are very crucial for the network.
So two more comments. In principle, if the signal is not so noisy, it is possible to get a result even for higher. So if the layer, for example, is at 8 kilometers and then the signal is decent, so the noise levels are decent above
that,
then you will get something. But
this is in general the case.
yeah, but if you have a layer at 14 kilometers, then noise is a problem, and I wouldn't do a relay fit for this case at 20 kilometers. It is too risky. Usually, it depends also on the noise levels of the signals, how much you average, but it can be risky. In that case, maybe it is even better to just use a reference height that is below and then do a forward inversion. If you're using, if you are having Raman backscatter signals, then forward in GLET is not a problem. For forward Raman is not a problem if you have a good reference height.
But then this is only for nighttime. You cannot have this for daytime measurements, or you cannot have it when they're in higher altitudes because the Raman signal is not so strong at 10 or 40 kilometers.
Yeah,
at 10 kilometers, you don't expect to have a good Raman return.
Yeah. At some point, it might be also interesting to apply a SIM for elevated layers and generate products just for them. For example, use these transmission techniques just get the coarse information on the layer that is high elevated, stratospheric, and so on. But now, right now, it is not. Yeah, it's not the specific target of SEC. It's not in the objectives.
And one last question, Nico. You mentioned about the meteorological data that radiation data are included in your software. In Atom Access, within the next year, we will have meteorological data from ECMWF, which will be processed in SEC for the retrievals, for the actress retrievals. Do you think that this data could be somehow provided also to the EarthNet community, to the actress community, in order to be used for this for these comparisons?
Yeah, this is a good idea, Eleni. It would be good to be able to fetch more radiation data, or not radiation. It can also be a model, as you said. This MWF is just a very good substitute for meteorological data. It would be great if we could have these values available in a database or something, and then when processing a measurement, just pick up the meteorological data for the specific station and for the specific time that the measurement
If
was.
the user doesn't provide any radiation data, how Atlas is handling this? Does it use a US standard?
No, it provides an error message that it will not proceed for the LFE test. The rest of the test, I think it's not a.
But you can use radiation from another station. It's not. I mean,
Yeah,
across Taiwan.
if you want to, yeah. I mean, if you can use another radius on the. This is true. Yeah, make it force it to proceed. Yeah, this is true.
Okay.
But the standard atmosphere is not.
Yeah, it's just the optimum one. Yeah, of course. Okay. Just to keep it short, should we close the session if no other questions exist? And of course, Nicola, we can invite you again.
Anna has a question.
Very quick one, because yeah, I pretend to do polarimeters now, so I don't follow the active discussions. But the Atlas would be, as I understand it, prerequisite. Like, we will have to pass our measurements and quality assurance test through Atlas in the future in order to submit it to SEC and have the retrievals. If it's not like that, can we still use SEC and have quality assured data in the end in the database, or not?
I think SEC is open to the whole EarthNet. So these actress requirements and so on are only relevant to the actress stations. So the stations that are affiliated with actress are within the main project. They also get funding from actress. They have to pass some. So the system has to be labeled that they are. In concept, they are compatible with the actress standards, and then prove after they prove that the concept is within the standards, prove that also the data fulfill the standards, and they continue to fulfill them for the duration of the project. It's half year. So this labeling process is mandatory, of course, for the active stations because it's part of the project. For the EarthNet stations, it is optional. They can also, I think, the plan is that they can also apply for labeling, although the priority is always the actress station when under pressure, let's say. But they can do it, yes. I think it is not excluding them at all from the SEC. And I don't know what happens in the case of locked configurations, because the configurations for all active stations, I think, will be locked, and then the users will not be able to change them if they don't report anything new. So as from cars, we will gather information from the stations, and if something changes, then we update the RS people to make an update, make a new configuration for these specific systems. This is the plan.
Okay, so to pass our data through Atlas first before submission to SEC won't be mandatory, or Atlas will be incorporated somehow?
Atlas, so the submission will not be to the SEC, it will be to Carport.
Okay.
Portal for cars. Yeah, it is independent things. I just try to make the format compatible because planning ahead, at some point, like in 5 years or even more, these things could these tests can also be implemented in a single calculus chain slowly. Yeah. So
Okay. Thank you.
Okay, thank you, Nico, very much
Thank you, Nico.
for the interesting discussion.
and thanks a lot for inviting me. It was a pleasure to give the presentation today.
Okay. Good luck with Atlas.
Thank you. Yes,
Thank
we
you.
are looking forward for the improvements there, and so that we can actually use it. And we will be in contact when we start using it. Then you can. Then I guess we will have questions.
Feedbacks.
We will need feedback from you there.
I'm looking forward for your feedback as well. Features that we will implement in the near future and hopefully before the training is cloud masking, simplistic cloud masking. So not just for to throw out coarse clouds. And also the rally fit. I will try to implement the code of Folger.
Okay, Nico, thank you.
Thank you.
Thank you. See you.
Bye.
Thank you, guys. Bye.